Good evening. Let's talk about isoelectric focusing. Right. So, when it is about separation of biomolecules, particularly proteins, and that too in presence of electric field, that is in electrophoresis. Right. There are many methodologies they have come up to reduce the complexity of samples to prove the physiochemical properties of such molecules. Now, when we say proteins and peptides, these are the class of molecules which are highly studied, and there are various methods by which we can study it, say agarose and polyacrylamide gel electrophoresis. Then advancement in the field are 2D gel electrophoresis, capillary electrophoresis, isotachophoresis, immunoelectrophoresis, and so on. So when I say about immunoelectrophoresis, it provides separation of ampholytic components, molecules that act as um, ampholyte. That's in, it has got both the properties ampho, amphi, right? So on lysis, it is going to work as a weak acid or a weak base, right? So on ionization, it is going to donate or donate or receive an electron. Accordingly, protonation or deprotonation are the phenomena we know. So the molecules or components which are going to demonstrate both the properties can act as a weak acid and a weak base, are referred to as ampholytic components. So in isoelectric focusing, ampholytes are used. They travel according to their charge under the influence of an electric field. So, is it not same like electrophoresis? Yes, but the additional point is they move under influence of electric field in the presence of a pH gradient, and they will move until the point they reach within the gradient where the net charge on that molecule would come to zero. How it can happen? Of course, it has to do with the point, that is isoelectric point. So when we consider peptides or proteins, the demonstration is according to the composition of amino acids, the charge residues that are exposed, and how that are going to act, whether they are going to behave as a weak acid and or weak base. So migration of such ampholytic species, of course, is going to be according to principle of electrophoresis. However, the mobility will change in presence of the pH gradient. So, how it will get changed? That is, the migration of the analyte will slow down and will come to a stop as it approaches the pH, which is same as its PI value. So, isoelectric focusing is going to be the advanced technique, you can say, where electrophoresis is used, and separation is on the basis of, for mainly, the charge, where the net charge come to an end, that is net charge is changed to zero, and this can happen under the influence of the pH in which it is getting separated, right? So we have to talk in details about that. When we talk about history of isoelectric focusing, the work was started by AGP Martin, and several contributions he has made in the field of electrophoresis. Martin also contributed in the field of chromatography, and he is the one who has been awarded Nobel Prize for all his efforts in biochemistry studies. All right. Um, of course, the work by Martin and Rigetti, uh, they are very important when we talk about separation of biomolecules by electrophoretic methods. And particularly when it comes to isoelectric focusing, yes, very immense contributions are made by these scientists, right? Now, let's come back to today's discussion, where I want to share a slide with you. Yes. Now, what do we see in the slide? It is the EPO abuse in athletes. That is what is the you can say a news. It was a news earlier, or in most of the international games, you find such news. They appear in the newspapers, and there is always a kind of conflict about who is the winner and why he or she should be not mm, uh, not a deserving candidate, or even if they win, is it because of the influence of the activators they have taken in through the injections, right? Now, when it comes to REPO, of course, what it has to do with electrophoresis. Let me talk to you about REPO. Uh, is banned by the Medical Commission of the International Olympic Committee. The anti-doping tests currently used, they cannot detect uh, to the degree of efficiency, you can say, or it cannot be detected with the confidence, because this REPO contained in the plasma is going to remain for 4 to 13 hours, and the biological effects would be seen or will occur several days after the treatment. So, if that athlete has taken any doses of these activator molecules, or you can say the drug molecules, who are going to improve their efficiency beyond human levels, and then they cannot be quantity of that drug may not be detected, but the effects are long lasting, and the performance of the athlete can be improved. So, what it has to do with isoelectric focusing, right? Of course, isoelectric focusing is proposed as a reproducible and reliable method for finding out the anti-doping agents, detection of these agents. Okay, so when it comes to the scenario where athletic performance and hormones are talked about, isoelectric focusing has to be the connect or the ultimate method for detection. So, yes, isoelectric focusing test is expensive and time consuming, but it is a method that is proposed by WID wide, and it is accepted as a method for detecting such abuse. So, the sensitivity of the method is really good. So let's talk about the case in 2003, where when the subjects who had received 9 injections of 50 international units per kg of body weight of epoetin alpha, right, they were tested for the presence of this molecule in their blood sample, but they were tested positive only for 3 days after the last EPO injection was given. However, on the seventh day, after last EPO dose, approximately, REPO dose, approximately half the subjects were still detectable. Now, what is this REPO? So, epoetin that is produced naturally and epoetin that is produced by recombinant method. The one that is produced by recombinant method is referred to as REPO. So, when the molecule which is available on the market is generated by recombinant methods, it is referred to as REPO, and when that dose is taken, then it remains detectable in the plasma for longer time, right? uh, uh, in spite of difficulty in the beginning, and of course it was really unsuccessful certain times to find out this REPO doping during Sydney Olympic Games. You must be remembering that. But ultimately, this isoelectric focusing was the method that was imposed as the official test, and that was recommended by the World Anti-Doping Agency, that is WADA, WADA, for screening of epoetin that is designed or produced by recombinant DNA technology or recombinant EPO, right? So, REPO abuse in athletes, if it is to be detected, isoelectric focusing IEF is the accepted method. So, in 2001, the first positive REPO doping case was uh, mentioned, and I think it was Danish cyclist Hamburger Bob who was charged for it. So, of course, it was not like directly the results were accepted, but it was brought in front of the Court of Arbitration of Sports, that is CAS, Lucerne. And at that time, discrepancies were there because the same sample was tested between two labs, the one lab at Lucerne and another at Paris. And mm, the criteria that they had set as standard value. So, according to one lab, they had requested 80% of EPO bands when it is electrophorest in the gel, and Paris lab, they had set the limit of 85% bands, EPO bands, that are to be located in the basic area of the gel. So there is inconsistency that resulted in the loss of the case and underlined the fact that positivity criteria had to be harmonized between the laboratories. Of course, after some years, this method was that was IF method, and these standards, they were what you can say harmonized, normalized, and so nowadays this method is accepted as a standard test for detection of EPOs, eponetin, that is recombinantly designed. So, what is this isoelectric focusing that we have to talk in details, right? So, let's talk about it, right? Now, when I have to talk about isoelectric focusing, I also have to say something about limitations of SDS and page. We have discussed in previous lecture what are the benefits of SDS page, but of course the limitations are mm, uh, deliberate denaturation of proteins prior to electrophoresis. Right, SDS is going to denature the protein, so that is one limitation or disadvantage, you can say. Enzymatic activity, protein binding interactions, detection of protein cofactors, etc., cannot be generally determined when you are uh, studying the protein with SDS page. So you have to have some methods which are what you can say are going to retain the native conformations, and alternative method is blue native page technique, right? That is what we had referred to in the previous lecture. Similarly, when resolving n number of proteins or their similar structural forms, isomers, that is a test or a case, then you cannot just complete the analysis with the help of SDS page alone. There comes in the play 2D, that is two-dimensional gel electrophoresis, and in this, one of the method, two dimensions. So first dimension is achieved through isoelectric focusing, and then you follow SDS page. So, when you are talking about dimensional gel electrophoresis, a technique is that initially you are going to separate proteins in a mixture with the help of isoelectric focusing, and then it is done with SDS page. So, you are exploring both the properties, that is the mass and the charge. So, it is one of the known methods and promising method in the proteomics, and it is used for study of diseases and protein isoforms and many more things. We will come one by one, we'll talk about the examples also. So as you are seeing in the schematic diagram, initially you are separating the proteins by isoelectric focusing. These arrows indicate the pH value that matches with the pi of the analyte, and it has stopped migrating and it has formed a zone. You can see the color spot here. Another color spot at pH 5, then at maybe 5.3, and then another is at somewhere 8, and so on and so forth. So what is this? How it gets separated? That we have to discuss. And once this gel has been run, it is overlaid on another gel for resolving the proteins on the basis of their mass, and that is by SDS page. So this is two-dimensional electrophoresis. When you talk, isoelectric focusing comes first. Now let us discuss about isoelectric focusing in details. Now here I'm sharing another slide that talks about 2D electrophoresis, of course. We will discuss that first, and then we will go to isoelectric focusing in details. So in the first step, the protein is separated into its charges with IF on the basis of charge with isoelectric focusing. And in the second step, the protein is separated according to its mass. And then the separated protein on the gel with IF, when you are talking about the second step, that is SDS is applied. So all the protein is charged negatively by the treatment of SDS, and then it is electrophorest, right? So the proteins that are focused on the first gel, that is on the basis of isoelectric focusing, they are then further separated according to their molecular weights. So when it comes to visualization of such separated proteins, generally staining methods what are used that we have to talk about. So when we talk about the gels, which are either 20 centimeter by 20 centimeter large gels are used in SGS based setup generally, and more than 10,000 proteins can be separated on such a gel. So, of course, another beauty of the technique is that even if the quantity of the protein sample, that is around 10 nanograms, is enough to give you the data and efficient analysis. Of course, as in case of protein staining methods we have talked in SDS page, here also Comasi dye is used if the protein amount is around zero point 0.5 nanograms, or else you can go with silver stain or fluorescent stains for efficient detection of the separated bands, right? So the technique that is commonly used, or you can say the system that is commonly used, where SDS and IEF both are carried out simultaneously, is referred to as ISO DALT, ISO DALT. That is what you can remember as one of the systems that functions wherein both these systems are working parallelly. Now let's go in details about isoelectric focusing. Here is the schematic diagram that shows you have cells or tissues from which you have extracted the proteins. Maybe these proteins are radioactively labeled or fluorescently labeled, it depends. Then this protein extract, you have to, of course, when you say protein extract, it is totally free of all other unwanted or contaminating molecules, that is very sure. And then you have to separate it. So you are going to take it to isoelectric focusing. So a long strip of the gel is there on which you are going to run the gel. Of course, it's a gradient gel. How it is prepared, we will discuss next. And then this gel strip is loaded onto second gel, which is the resolving gel, and it is going to work as per SDS page method. But here, if you notice, the directions of electric current are different. Here it is horizontal, here the arrow is vertically downward. So two opposite directions it is run. So once second dimension is allowed to run, proteins are allowed to run in the second dimension, electrophoresis is done. You have to stain it, or you have to expose it to X-ray films. Of course, you can extract the spots and further go for analysis. So the principle of two-dimensional gel electrophoresis, when you talk about the overall methodology or this approach, uh, can really be used for thousands of different proteins in the extract, and they can be very well separated into individual spots. As you can see in this gel, you can see n number of small and big dots of different sizes depending upon the concentration and quantity of that particular protein in a given sample, right? So let's go to the next slide, right? Here is the enlarged diagram that shows uh, the 2D gel electrophoresis, right? So here you have IF of proteins on the IPG strip, right? Isoelectric focusing gel strip that is done, and in gel enzymatic digestion of selected protein spots is done. Of course, that is the advancement of it, which is required for further analysis, where you are going to use MS, mass spectroscopy, that is attached to it for analysis. So that is the next part. So advancement for analyzing the gel can be documented, it can be the data can be compared with the existing libraries. But further, when you are going to analyze each protein which is present in each band, then it can be extracted, the spot is extracted, and further you are going to go with enzyme assays, purity detection, so on and so forth. And of course, analysis can be completed with the help of MS analysis, right? So this is one way. And A further advanced method is referred to as multiple channel electrophoresis, you can say. So here you are going to have enzymatic digestion of proteins, then you are going with the pH gradient, that is isoelectric focusing, and then it is going for MS analysis. But in addition to this, you can go on with MCE technique, where you are going to separate the two proteins as two separate bands, and they are fractionated according to their pi. Separated peptides are they are detected by mass spectroscopy, and separation of peptides of proteins in a MCE channel or OF gel is followed by analysis via mass spectroscopy. So this is another in between step. So these are just to make you understand the flow chart of the process, where which can be useful for schematic representation of the technique. Now let's come back to the point, that is isoelectric focusing is based on pi value, that is what we are talking, right? That is the isoelectric point of the protein. So as we have talked, ampolyte or amphoteric components, they have both the groups which are going to have their independent charges, like positively charged groups and negatively charged groups, say example of amino acids. So if they cannot be detected, the components those cannot be detected by conventional electrophoresis can be made detectable using advanced versions like IF, and followed by then SDS page further. So separation, when you are talking, is based on a pH gradient in the gel, right? So gel is not a single polyacrylamide gel, but there is gradation with reference to the pH. So you have zones of the gel where the pH is going to be different. How it is generated, that we have to talk. So ampholites are added to it. So amphoteric components are separated, and ampholites are the substances which are added into the gel, so that they are going to impart particular pH to the to the gel. So when you are talking about isoelectric focusing, the charge on amino acid side groups, right, is going to be dependent on the pH of the surrounding solution, we know. So proteins will migrate to a point in the pH gradient according to its molecular size. It will be moving. No, it is mainly, now here is the basis is the pH, right? So gradient is corresponding to its isoelectric point or pH. The protein will move in that gel, gradient gel, and when the pH of the surrounding solution matches with isoelectric point of the protein, the net charge will become zero, and protein migration will stop. So now, for example, in this, you are able to see that the pH here is about 7.8 something, which is the pi value for the protein under study. So the net charge, if you talk about, is zero, and the migration of the analyte will be stopped. Now here, when I talk about proteins, let's discuss about the positive charge and negative charge, how it is there. So isoelectric point, when I say, uh, or amphoteric molecule when I say, zwitterionic molecule when I say, examples as we know are amino acids, peptides, proteins, etc. Now let's take example of amino acid. The isoelectric point is how it is calculated, right? So it is about ionization of the charge groups on the molecule. So that is the indicator for that is pK value, dissociation constant of the molecule, of the charge group on the molecule, right? So you can have pKa values for amines, and pKb values for carboxyl group, like that you can talk about it. But of course, one protein is going to have multiple amino acid, and each amino acid may have more than one functional group which are ionizable in solution. So for example, if you take lysine, it has got two amino groups, or if you take example of aspartic acid, it has two carboxylic groups, so acidic groups, right? So you have to find out the pK value. So each group is going to undergo ionization. So it is going to have more than one pK values, right? So it is going to have two groups, so two ionization points, so two dissociation constants, so two pK values. So when you want to find the pK of any uh, 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 amino acid, for example, it is done by titration, right? But when you are talking about isoelectric point, then it is given by the pK value. So if there are two pK values, you have to take the average of it. So average of the two pK values of the acid. When you are talking about say aspartic acid, you have to take the value for both the functional groups. Two acidic groups fine, but each of these acidic is going to get ionized under different points, and the pK value at that time is going to be different. You have to take the average of the two, and that will be the isoelectric point for that particular amino acid. So similarly, you have to find out the pi for peptides and proteins, so which is nothing but you can say the total basic or acidic character of a zwitterionic molecule, right? So compounds with pi value greater than 7 can be considered as basic, and those with pi value, that is isoelectric point, less than 7 are considered as acidic. So the isoelectric for a simple amino acid, the pi can be obtained using the average pK1 and pK2, where pK1 refers to the acidic group and pK2 to the amino group, right? Both have to be taken into consideration. So the value also can be obtained experimentally. Of course, the electrokinetic experiments are to be conducted to evaluate the partial charge on the molecule, and you can find out the pK values and pi values for that molecule. So this is just to give an overview of the concept pi. Then now here, when I'm talking about the isoelectric focusing method, then pi value of peptides or proteins can be determined by capillary electrophoresis, right? So in this case, electrophoretic mobility of the protein or a peptide is measured at different pH, and then the obtained values are then plotted as function of pH. So on one axis you have pH, and on another axis the dependent variable is the mobility of the protein. What is mobility under electric field? How it is calculated? What is mu? What is V? All this we have discussed in the first lecture while talking about in the introductory lecture about of electrophoresis, right? So you know what is the electrophoretic mobility is. So electrophoretic mobility at different pH is measured and the graph is plotted that would give you the value for pi. Right. So you can find out the isoelectric point of peptide or protein from these plots. So here you can take the help of CIEF technique or CE method, which are important. When I say CIEF, it is capillary isoelectric focusing, and when I say CE, it is capillary electrophoresis. So capillary electrophoresis, the gel is of one type, uniform gel, but when we talk about capillary isoelectric focusing, of course you are going to have better, higher resolution because you are using a gradient gel. So in that gradient gel you need to add the ampholites. So ampholites, they are added to the gel, a voltage is applied to the gel or the capillary, and the ampholites will migrate through the gel or capillary on the basis of their net charge, and then they will establish a pH gradient in the gel or capillary. So ampholites will migrate to a point where uh, uh, they are going to in specific concentrations they are used. So gradient gel is prepared by adding the ampholite, and then uh, uh, your sample analyte is added to that capillary electrophoresis system. The advanced version of capillary electrophoresis system is microchip based method, which is an alternative to capillary electrophoresis. Fine. So this is uh, just some insights into the method. Now here when I say ampholites, what are they really? So of course, as we have molecules like the polyamino sulfonic acid, for example. When I say polyamino sulfonic, so sulfonic is one, amino is another group, positive charge, negative charge. Or here you are able to see that is amine group at one end and carboxyl group at the another end. So these are ampholite molecules, right? So Ampholytes are the mixture of compounds that are used to establish a pH gradient in IF. Right. So as you can see here, this is the gel. This is the gel pH that is generated by migration of these ampholyte molecules under upright field, and they will set a gradient. And on this, the protein will move across such gradient gels and will get separated in form of zones, and the zones are formed when the protein stops migrating. The protein will stop migrating when its pi value matches with the pH of the gel. So you have to prepare the gradient gels and then run the protein on that. Now here are much some more details about. Of course, I'm not going to go in these details right now. Let's talk about advantages and disadvantages of isoelectric focusing. So when I talk about precipitation of high concentration of proteins at their pi, right, because of the net neutral charge, then the point is that there may be certain overlaps, right, between the fractions, and you may not have efficient separation. The ampholytes that are used to establish the pH gradient may interfere with the subsequent analysis when you are going with electrospray ionization for mass spectroscopy. So ampholytes may interfere the process. So to avoid this problem, the protein fractions can be dialyzed. So you have to, once the sample is run by 2D electrophoresis or isoelectric focusing, then you have to extract the spot, then you have to extract the protein out of the spot, and then you have to dialyze the protein so that these unnecessarily ion groups, they are removed, the ampholyte groups are removed, and then you can go for mass spectroscopy. Right. Of course, dialysis is one method. Another is chromatographic methods are there to remove the ampholytes. So gel exclusion chromatography, where on the basis of molecular size, you can retain the proteins and the small I mean, the proteins will elute out first and the ionic groups will be retained in the gel. So, depending whether you are using a dialysis system or gel exclusion chromatography system, you can uh, avoid the problem that is caused by presence of ampholytes during further analysis, that is ionization, electrospray ionization mass spectroscopy. Right. Now, when to talk about applications of isoelectric focusing cell, the proteins are migrating to a position in the established pH gradient that we have seen. The advantage is that a complex mixture of proteins can be fractionated according to their pi in a non-gel medium also, right, and the fractions can be collected and analyzed further. So it is very efficient method for separation of proteins which cannot be easily separated or fractionated when it comes to single dimension electrophoresis. So you have to explore another thing, that is the charge isoelectric focusing based on pi value, and then in the second dimension you can take it for SDS page, right? That is how you can talk about two-dimensional gel electrophoresis. Now, when you are doing two-dimensional gel electrophoresis, that time isoelectric focusing, when I have to say, I just have to summarize certain points and then we will go to next. So when I talk about this method, isoelectric focusing gel, they are ideal for separation of amphoteric substances, right? We have seen that they are very important or ideal, you can say, for separation of amphoteric substances, because the separation of molecules is occurring according to different isoelectric points. So this method is having good resolution, and it is able to separate proteins that differ in their isoelectric points by a difference of as less as zero point zero 0.01 of pH unit. So if it is 1.11 and 1.10, a protein, one is the first in the mixture. If you are say two proteins, first protein is having pi value as one say 5.57 and another is having 5.58. They cannot be separated by simple electrophoretic methods. Molecular size wise, if they are same, then a simple SDS page is not going to be enough. Single gel electrophoresis is not going to suffice the requirement, but isoelectric focusing can separate because the efficiency is as high as the point that if the isoelectric points they are differing just by 0.01 pH unit, 0.01 unit difference, those proteins also can be separated by IF. So generally when you talk about IEF systems, horizontal gels on glass plates or plastic sheets, they are commonly used, and separation is achieved by applying a potential difference across the gel. The pH gradient is formed, as we discussed earlier, by addition of compounds which are known as ampholites. So ampholites are nothing but complex mixtures of polyamino polycarboxylic acids. Polyamino polycarboxylic acids. We have seen the structure of these molecules right here in this slide. So ampholites can be purchased. Of course, they are available in wide range from pH 3 to 10, and for narrow bands as well, as that is, if you want ampholite between pH 7 to 8, they are also available. You have to choose the right one according to the isoelectric point values of your sample, and then you can include these biolites or pharmalites as they are called as and available on the market into your gel. So when you're talking about the gel properties for isoelectric focusing, generally 1 millimeter to 2 millimeter thick isoelectric focusing gels are used. When it comes to research work, commonly 1 millimeter to 2 millimeter thick gels are used. But when you talk about the ampholites, they are relatively costly molecules. So whole entire process is expensive procedure. Of course, when you talk about thin layer isoelectric focusing gels, which are even thinner, I mean less than 1 millimeter. So how thin they are? So it is, say, when you talk about thin layer IF gels, they are 0.15 millimeter thick, and they are used um, in the process. And how are they prepared? They are prepared using a layer of electrical insulation type as the spacer between the gel plates. And it is very important because as the size of the gel has reduced, the quantity of amphollite required also is reduced, and it has become comparatively cost beneficial method. Of course, uh, uh, in this method, the proteins have to move freely according to their charge under the electric field, right? So IEF is carried out in the gels where the percentage of the gel should be such that you should not have sieving effect, right? So pore size should be good enough. So quantity of the gel, polyacrylamide gel that is commonly used must be such that it should avoid the sieving effect if any would get generated. So generally 4% polyacrylamide gels are commonly used for isoelectric focusing, right? Agarose also is used in certain cases for isoelectric focusing, and agarose is specially used if the molecule size of the proteins under study is high. So when we are talking about the polyacrylamide gel, the proteins having high molecular weight may undergo some degree of sieving even in low percentage acrylamide gels. So in such cases, agarose is used as a gelling matrix, right? These are the few technical terms, technical points that we need to discuss when it is about isoelectric focusing. Now, when you are preparing a thin layer IF gel, these carrier ampholites of a suitable pH range that you have taken, they are mixed, and riboflavin is mixed, and this is mixed in the acrylamide solution. In the previous lectures, we have talked about how polyacrylamide gel is prepared, how that cross-linking is facilitated. What are the methods? Chemical method and photochemical method. In photochemical method, we have photo decomposition as a base, and riboflavin is the catalyst used. So you are going to mix this riboflavin, the ampholites, and acrylamide together, and the mixture is then poured into the system. So you have to pour it in the over in the I should say over the glass plate, and the glass plate are generally 25 centimeter by 10 centimeter when we talk about common laboratory research page instruments when we talk about. So 25 centimeters by 10 centimeter, and of course spacers are there So the second glass plate is then placed on the top of the first to form the gel cassette. So once the cassette is ready, that means once the gel is polymerized, of course, photopolymerization, when we talk about riboflavin, is happening. So the gel, once it is poured between the glass plates, it is placed in the front of bright light. So photo decomposition of riboflavin will generate the free radical, and it will initiate polymerization and cross-linking of acrylamide and bisacrylamide. We know that it takes about 2 to 3 hours, right? Once the gel has set, the glass plates are removed, and the gel is stuck to one of the glass sheets of the two, right? Then the electrode wicks, which are generally 3 millimeter strips of filter paper, and the anode is phosphoric acid and the cathode is sodium hydroxide that can be used. Then they are laid in the along the length of the gel on either side, and then you are going to um, apply the electric current. Now potential difference is going to get generated, and the ampholites will form a pH gradient between the anode and the cathode. So once you have set the gel, you have to apply the current, let the ampholites migrate, let the ampholites form the pH gradient, and then you are going to turn off the power. Then you are going to apply the sample on the gel, and the filter paper wicks that are soaked, you are going to use, or maybe you are using the gel strip, which is where you have what say the proteins separated earlier by single dimension electrophoresis. So maybe the protein is on the paper strip, or maybe it is in the buffer solution, or maybe it is in the uh, gel strip, right? So you are going to apply it, and then voltage is again applied about 30 minutes. So the samples will electrophorese off the paper, they will come onto the gel, or from the base gel strip to the main resolving gel. We have seen in the previous lecture that you have stacking gel and you have resolving gel. So in stacking gel place, you can put samples to concentrate, right? Here you are applying the sample where in the form of spots on the gel or spots on the paper, and then once you give a small pulse of current, say about for 30 minutes, they will run up from the paper or from the gel, and they will come in the playground, that is the resolving gel, right? And then they will start migrating, and they will, depending upon the point at which the pH gradient of the sample and that of the protein are going to be matching, then it will stop migrating. Now the point at which the pH gradient of the sample where you have loaded it, the proteins are initially at pH region below their isoelectric point. So when you are loading the spot, it should be at a point that is below the pi value of the protein under analysis. That is very important. So at that time, uh, below their isoelectric point, if you are chosen the pH which is below the isoelectric point of the sample, then it will be having net positive charge, and it will migrate towards cathode. So this is very important to remember, that when you are applying the sample, loading the sample, the proteins that are initially at a pH region that is below the isoelectric point, so it will carry net positive charge, and it will move towards cathode. As they start moving, the surrounding pH will be steadily increasing, because you have generated gradient by adding the ampholites, right? So increasing, and the positive charge on the protein will go on decreasing then, and it will go on decreasing until eventually the protein is going to reach to a point where the pH is equal to its isoelectric point, and as a result, the net charge will be nullified to zero. Now the protein will be in the Zwitterian form with no net charge, and the movement under electric field will stop or will cease. So substances that are initially at pH regions above their isoelectric points will be negatively charged, and they will migrate towards the anode. So you are going to have a system isoelectric focusing when you are talking about. Then, as you can see in the diagram, one side you have positively charged electrode, another side is negatively charged electrode. The movement of proteins is under the influence of ampholites, or the pH gradient is going to be dependent on the net charge on the protein, right? So when it is in the region where uh, its pI is more than the pH. So pH region is below the isoelectric point. Then it will have positive charge. And if it is in the region where the isoelectric point is more, or the pH is more than the isoelectric point, you have to see there are two things: whether the pH region in which the protein is kept, that pH is below isoelectric point, then the protein will have net positive charge. And if the pH region is more, is having higher pH than the isoelectric point, then the protein will have negative charge. So accordingly, the movement towards anode or cathode would be occurring. The protein will be in the deuterium form, it will come to net charge 0, then it will stop moving. But this, for this to happen initially, and the proteins will be migrating in both the directions depending upon their pi values. So some of them will move to cathode, some of them will move to anode, and that migration will happen or go on until they reach their isoelectric points and become stationary. Now, uh, it is generally observed that sample always move towards their isoelectric points if it is not critical where on the gel they are applied. So whether to apply it in the starting point, in the center, on the side or left side, it is not going to be very critical, because they are always going to move to the point which is going to be towards their isoelectric point, the pH that matches with isoelectric point. So it is observed that the samples always move towards their isoelectric points. So you can load the gel and start the electric current. Movement will happen in the direction of isoelectric point. Now, generally, when we talk about rapid separation methods, 2 to 3 hours relatively at higher voltage if you are running the system. So, when I say higher voltage, then it is about 2500 volts that is used, and separation of proteins may take 2 to 3 hours in such cases. Remember, we are talking about a gel plate where you have the dimensions 25 centimeter by 10 centimeter. So, size of the gel and the time and voltage, these things are interdependent. So you have to choose the system. I'm talking about a system where it is typically 25 centimeter by 10 centimeter glass plate, and then you're talking about the gel where you are applying high voltage up to 2500 volts. It will take about 2 to 3 hours. Of course, when you are applying such a high voltage, heat is going to be produced. So gels are generally run on cooling plates. That is another important component. So cooling plates are the plates which are at a lower temperature, say around 10 degrees Celsius are there, right? Now when I say this 10 degrees Celsius, that means cooling is there, and it is going to help the entire system. So denaturation of samples will not occur, overheating will not occur, migration will not be affected due to temperature, so on and so forth. So the gels are run on cooling plates. And of course, power packs are used to stabilize the power output. So thermal fluctuations will harm the process, will affect the efficiency. So stabilizers also are important. So following electrophoresis, the gel must be stained to detect the proteins. Right? We have talked about it earlier also, how the gels are mm, uh, uh, stain. So we have either Comasi brilliant blue stain, or we have the silver stain, etc. So first we have to fix the gel, right? We have talked about it earlier. Then you have to stain the gel. So when we talk about this isoelectric focusing gel, it is first washed with fixing solution, and the fixing solution is nothing but 10% trichloroacetic acid. So because of acetic acid, the proteins will get precipitated in the gel, and most of the amphaloids will get washed out. The smaller amphaloids, the those which are used to create gradient, if they are there, they will get washed out. And the precipitated proteins in the gel, then they are stained with Comasi brilliant blue, with a typical method that we discussed earlier. Fixation, staining, destaining, washing, destaining, etc., and then docking system. So uh, the so that you get the colored spots, right? So the pi of a particular protein you have to remember that it is to be determined. So that can be determined conveniently by running a mixture of proteins of known isoelectric point on the same gel, and number of mixtures of proteins with different pi values they are available. So when you run it, it is going to act like a standard or reference proteins, and then depending upon the distance of migration, you can find out the pH at which it stops migrating, and then comparing with the reference proteins, you can find out the pi value for a given protein. Of course, staining is required, and after staining, the distance of each band from one electrode is measured, and graph of distance for each protein against the pi value is plotted. I repeat, the graph is plotted that of distance of each band from one electrode, and uh, is measured, and graph of distance of each protein is plotted against its pi, right? So you can have the calibration line, and the pi of an unknown protein can be determined from its position on the gel. So if you don't know the pi of the protein under study that you are handling, then you can purchase the protein samples which are available on the market with known pi values, and that mixture along with your sample all are run on the gel, and depending upon the distance migrated by individual band and that by your sample protein, you are going to measure it, plot a graph of that against pi values which are known for the reference proteins, and then you can have a mm, uh, uh, estimate for the pi value of the unknown. So isoelectric focusing is one of the very important techniques individually also for electrofocusing of the proteins, and second for better resolution as a component of two-dimensional gel electrophoresis. Right. So with this, the overview for gel electrophoresis with reference to IEF is done. We may continue in the next lecture.